I am recording. Okay. So, let's start at the top. Conditional probability. Conditional probability is finding the probability of something given that another thing already happened. For example, if I said to you, if you couldn't look out the window right now, and you didn't know what the weather was like, and I said, what's the chances that it snowed? What would you say? You'd be making up a subjective probability, right? Just making something up. What would you say? Andon? A 90% chance? Okay, so we're saying that you don't know what the weather is, Andon. So if you don't know what the weather is, Triton, what do you think? 50%? Because it's early December. Okay, so maybe you'd say a 50% chance outside that it snowed. Now, what if I said to you, what are the chances that it snowed outside, given that we hear this noise right now? 100%, because we can hear the snowblower going, right? We can, okay, it was so loud right before I said that, right? And then as soon as I said it, it was like, turn it off, turn it off. She's using us as an example. So anyway, you can hear the snowblower going. So you know, okay, now I know for certain that, you see how like just one thing given can really change your probability about something? That's what a conditional probability is. It means that you've had a condition, as in like, here's the condition that happened, and now we've got a different probability. That make sense? So this means you're finding the probability of A, probability of B, given that A already happened. So for example, this would be, what's the probability that there's snow outside? Remember how P just means probability? What's the probability that there's snow outside given that we can hear the snow blower? So the second thing is the given thing, and the first thing is what you're trying to figure out. Do you guys understand the notation? Okay. For example, two cards are selected in sequence from a standard deck, not form. Find the probability that the second card is a queen, given that the first card is a king. All right, so I want you to imagine that there's 52 cards in front of you. And I take a king, I draw it, and I got a king, right? And then I throw the king away. I'm not it says assume the king is not replaced. I'm not replacing the king. What's the chances that I draw a queen now? Colin? Yes. How many queens are in the deck? 4 out of how many cards are in the deck? 51, because I threw that one card away. So this is the conditional part, that 51 is the conditional part. Do you feel like you guys understand? All right, now, I'm very sorry that when I made copies of this that it got so hard to read. So if you want to add to it, you can write, this one says Jean present. This one says not present. This one says total. This one over here says that it's a high IQ. This one's a normal IQ. And a total. This, by the way, is actually what I specialized in, combinatorics and permutations. When I went to college to become a math teacher at UW-Madison. They told us we could go, when you're a math teacher, you can specialize in one of two things. You can either go the calculus route, which is like more advanced math, calculus, that kind of stuff, or you can do the statistics route. And I chose the statistics route. I mean, I had to take through calculus 3 automatically, which is a lot. I took 11 math courses in college. But I also then focused on probability and statistics, which I prefer because I think it's fun. All right, and the table below shows the results of the study in which researchers examined a child's IQ and the presence of a specific gene in the child. Find the probability that a child has a high IQ given that the child has the gene. So we already know the child has the gene, right? Do you guys agree? We know that the child has the gene. So all we're thinking about is this column right here where it says that the child has the gene. We don't even care about the rest of this. Okay? It tells you where to look. So now that we know that the gene is present, what is the probability that they have a high IQ? 33 out of 72. So since we know that the gene is present, the probability that they have a high IQ is 33 out of 72. Do you guys see how that's very different than the rest of the numbers, right? If I just said, what are the chances that they have a gene present and a high IQ, you'd say 33 out of 102. But we already knew that they had the gene present, so. All right, your turn. Find the probability that a child does not have the gene, given that a child has a normal IQ. I'm going to give a prize for this one. I do have temporary tattoos that are a risk. We're doing some tattoo roulette here, okay? So you have to wear it if you win it, and it has to be somewhere visible. Not that all of us have a lot of exposed skin right now, except for, of course, Colin. Are you twinning with somebody?
Yeah.
No. I just thought maybe you're just into it today. So does not have the gene given that the child has a normal IQ. So we're looking at the normal IQ section, and then you're going to figure out the probability that they do not have a gene, given that it's a normal IQ. All right, hands up. 1, 2, 3, 4, 5. 3. Okay. All right, so it says the child has but the part that's given is that a child has a normal IQ. So the part we're going to look up, Andon, is just this. We're just looking at that row now. Is there a 30 in that row? No, then you can't use it. So what's the possibility that the gene is not present? Good, 11 out of... Did I highlight a 30?
No.
50. Did you say 50?
No, I said 30.
Okay. So, because it says that a child has a normal IQ, you only look at this row, okay? And then you pick out the thing from that row. Are we okay with this? Andon, what prize would you like? Go for it. There's also slime up there, and fish, and Hardware Hank Waters.